G'day, and welcome back. Today we're starting acids and bases. Now, this topic has a scary reputation, but here's a secret. The whole thing comes down to one tiny particle moving from one place to another. That's it. Once you can see that little particle changing hands, every equation in this topic writes itself. By the end of this lesson, you'll be able to define acids and bases properly, spot what we call conjugate pairs, and write correct, balanced acid-base equations, all the way up to ATAR level. Let's take it slowly, step by step. Before the theory, let's meet these substances the way people met them for centuries, with their senses. Acids taste sour. Lemon juice, vinegar, the acid in your own stomach. All acids, all sour. Bases are the opposite family. They taste bitter, and they feel slippery, like soap. In fact, soap feels soapy because it's basic. Oven cleaner and antacid tablets are bases too. Chemists use a dye called litmus to tell them apart. Litmus is just a color-changing indicator. Acids turn it red, bases turn it blue. Simple test, no tasting required, and please, never taste chemicals in a lab. But here's the thing. Sour, slippery, red, blue. These are descriptions. They tell us what acids and bases do, not what they are. For that, we need a theory. And the theory we use in VCE is a beautiful one. That's our next board. Here it is. The Brønsted-Lowry theory, named after the two chemists who thought of it, it's built on one particle, the proton. Now, a proton here just means H+, a hydrogen atom that has lost its one electron, so all that's left is its center. It's the smallest, lightest ion in chemistry. Think of it as a tiny ball. An acid is a proton donor, a giver, like someone handing over a ball. A base is a proton acceptor, a taker, the one catching the ball. That's the entire theory, giver, taker. Let's watch it happen. Hydrogen chloride gas dissolves in water. Look at the equation. HCl plus water makes H3O+ and Cl-. Follow the ball on the right side of the screen. HCl handed over one H+, so HCl is the acid. Water caught it, so water is the base. And that new particle, H3O+, is called the hydronium ion. Nothing mysterious. It's just a water molecule carrying one extra proton. Water caught the ball, and now it's holding it. Nothing scary here, just one tiny particle moving from one place to another. Every reaction in this topic is this same pass, with different players. Now for a word that sounds harder than it is. Conjugate. Conjugate just means linked together, like a pair of dance partners. A conjugate acid-base pair is two species that differ by exactly one H+, one tiny ball, nothing more. When an acid gives its proton away, whatever is left behind is called its conjugate base. And when a base gains a proton, the new species it becomes is called its conjugate acid, same particle before and after the pass. Let's find the pairs in our equation from the last board. HCl gave away one H+ and became Cl-, so HCl and Cl- are pair 1. Water gained one H+ and became hydronium, so water and H3O+ are pair 2. Every acid-base equation contains exactly two pairs, always two. And here's your checking rule, worth real marks. The two partners must have the same atoms apart from one hydrogen, and the one without the H+ sits one step lower in charge. Look at pair 1. HCl is neutral, Cl- is -1. One H gone, charge one step down. Perfect. If your pair differs by two hydrogens, or the charge doesn't drop by one, something's wrong. Go back and check. Time to build equations ourselves. 4 steps, and they never change. Step 1. Decide who's who. Which species is the acid, the giver, and which is the base, the taker. Step 2. Move exactly one H+ from the acid to the base. 1. Never two at once. Acids hand over one ball at a time. Step 3. Fix the charges. The giver just lost a +1 particle, so its charge goes down by 1. The taker gained it, so its charge goes up by 1. Step 4. Check your work. Count every atom on each side, then add up the charges on each side. Both must match. Let's run it. Hydrofluoric acid, HF, in water. Step 1. HF is the acid, water is the base. Step 2. One H+ moves across. Step 3. HF was neutral, so it becomes F-. Water was neutral, so it becomes H3O+. Step 4. Check. Fluorine, 1 each side. Oxygen, 1 each side. Hydrogen, 3 each side. Charge, 0 on the left. -1 + 1 is 0 on the right. Balanced. Lovely. One new symbol. That double arrow means the reaction runs in both directions at once. HF is what we call a weak acid. It holds its ball loosely, but sometimes takes it back. Strong acids like HCl throw the ball and never take it back, so they get the single arrow. Weak acid, double arrow. Strong acid, single arrow. Keep that rule close. Here's a lovely twist. Some substances can play both roles. We call them amphiprotic. Amphi just means both, like amphibian, an animal that lives in water and on land. An amphiprotic substance can donate a proton or accept one, depending on who it meets. The classic example is the hydrogen carbonate ion, HCO3-. Put it with water and watch it act as an acid. It donates its H+, becomes carbonate, CO3-2-, and the water becomes hydronium. But the very same ion can act as a base. It accepts an H+ from water, becomes carbonic acid, H2CO3, and the water, having given a proton away, becomes hydroxide, OH-. Same ion, two completely different games depending on its partner. And water itself is amphiprotic. We've already seen it act as a base with HCl. Put it with ammonia, and it acts as an acid instead. Water is the great all-rounder of chemistry. Now the exam tip. When a question says, show that a substance is amphiprotic, that is code for write 2 equations. One where it donates, one where it accepts. One equation gets you half the story and half the marks. 2 equations, full marks. Last concept. Some acids have 1 ball to give, some have more. An acid with exactly 1 proton to donate is called monoprotic. Mono means 1. HCl, 1. Nitric acid, HNO3, 1. An acid with more than 1 is polyprotic. Poly means many. And here's the rule the examiners love. A polyprotic acid gives its protons 1 at a time, stage by stage, never all at once. Sulfuric acid, H2SO4, has 2. Stage 1, it donates its first proton to water and becomes the hydrogen sulfate ion, HSO4-. This first stage is complete. Every molecule does it, so it gets the single arrow. Stage 2, HSO4- donates its second proton and becomes sulfate, SO42-. This stage is only partial, so it gets the double arrow. Notice something nice. HSO4- donates here, but it could also accept a proton back. It's amphiprotic. Everything in this topic connects. Phosphoric acid, H3PO4, has 3 protons, so 3 stages. Look at the staircase on the right. Each step down, the acid loses exactly 1 H+, and the charge drops exactly 1 step, 3- at the bottom. Every stage follows the same pattern. Water on the left, hydronium on the right. So here's the locked rule. 1 equation, 1 proton. Write H2SO4, losing both protons in a single equation, and you lose the marks. 1 ball at a time, always. Time to use it all. First worked example, nice and gentle. Nitric acid reacting with water. Which one is the acid? Which one is the base? We're given the whole equation, so everything we need is already on the page. We want the giver and the taker. The method is always the same. Follow the ball. Look at HNO3. It ends up as NO3-. 1 hydrogen gone, charge down 1. It donated. Now water. It ends up as hydronium, 1 hydrogen richer, charge up 1. It accepted. So the acid is HNO3 and the base is water. Box it. Done. That's the rhythm for this whole topic. Don't memorize which substances are acids. Just follow the H+ across the arrow, every single time. Second type, ethanoic acid, the acid that makes vinegar sour, reacting with water. Find both conjugate pairs. Notice the double arrow. Ethanoic acid is weak. It holds its ball loosely. We need 2 pairs, and each pair must differ by exactly 1 H+. Match the partners across the arrow. CH3COOH becomes CH3COO-. Same atoms, 1 hydrogen fewer, charge one step down. That's a legal pair. Water becomes hydronium. One hydrogen more, charge one step up. Legal pair number 2. Box them. Pair 1, ethanoic acid and ethanoate. Pair 2, water and hydronium. One small warning. Students sometimes pair the acid with hydronium because they sit at opposite ends. No. Partners must be the same species before and after the pass, 1 H apart. Always match across the arrow, like matching socks. Same sock, one hole. Now we build one from scratch. Ammonia dissolves in water and acts as a base. Write the equation. Step 1 of our 4 steps, name the players. The question tells us ammonia is the base, the taker. So water must be the acid, the giver. There's water being amphiprotic again, playing the opposite role to the one it played with HCl. Step 2, move exactly 1 H plus from water to ammonia. Step 3, fix the charges. Ammonia was neutral, it gained a +1 ball, so it becomes NH4+, the ammonium ion. Water was neutral, it lost a +1 ball, so it becomes OH-, hydroxide. Write it out, with states, and a double arrow because ammonia is a weak base. Step 4, check everything. Nitrogen, 1 each side. Hydrogen, 3 + 2 is 5 on the left, 4 + 1 is 5 on the right. Oxygen, 1 each side. Charge, 0 on the left, +1 - 1 is 0 on the right. Box it. 4 steps, no guessing, and the check at the end means you walk away certain. That certainty is worth more than speed in an exam. 4th example, and remember the exam tip from earlier. The question says, show that this ion is amphiprotic, that is code. Code for write 2 equations. One where it gives a proton, one where it takes one. First, let it act as an acid with water. It donates 1 H+, so it drops 1 hydrogen, and its charge goes from -1 down to -2. It becomes HPO42-, and water becomes hydronium. Check the charge. -1 on the left. -2 + 1 is -1 on the right. Balanced. Now the same ion as a base. It accepts 1 H+ from water, gains a hydrogen, and its charge rises from -1 up to 0. It becomes phosphoric acid, H3PO4, and water becomes hydroxide. Check again. -1 on the left, 0 - 1 on the right. Balanced. 2 equations, each moving exactly 1 proton, each balanced in atoms and charge. That is a complete proof and full marks. Notice this ion is one of the steps on our phosphoric acid staircase. Any middle step of a polyprotic staircase is amphiprotic because it can step down or climb back up. Once you see the staircase, you can answer this question for any ion they throw at you. The big one. This is where everything in the lesson comes together in a single ATAR question. Sulfuric acid in water. Both stages, correct arrows, every conjugate pair named. Breathe. It's just 2 passes of the ball. Stage 1. Sulfuric acid donates its first proton to water. It becomes hydrogen sulfate, HSO4-, and water becomes hydronium. Arrow choice, and this is the ATAR detail. Stage 1 is complete. Every molecule donates. Single, full arrow. Stage 2. Hydrogen sulfate donates its second proton, becomes sulfate, SO42-, water becomes hydronium again. But stage 2 is only partial, so it earns the double arrow. Mixing up those 2 arrows is the single most common error on this question. Now the pairs. Stage 1. Sulfuric acid and hydrogen sulfate, 1 H apart. Water and hydronium. Stage 2. Hydrogen sulfate and sulfate, 1 H apart. Water and hydronium again. Box it. 2 stages, 1 proton each, 4 pairs, arrows correct. And spot the star of the show. HSO4- is the conjugate base in stage 1 and the acid in stage 2. The middle step of the staircase, amphiprotic, right on cue. When you can tell that whole story, this topic is yours. Let's take all this into real life, into your own body. Your stomach is full of hydrochloric acid, genuinely strong acid, and useful. It breaks down food and kills germs. But make too much of it and it burns. That's heartburn. And chemistry offers a very elegant fix. If the problem is too much acid, swallow a base. That's exactly what an antacid tablet is. The most common antacid is sodium hydrogen carbonate, baking soda. Here's the reaction with stomach acid. Sodium hydrogen carbonate plus HCl gives sodium chloride, water, and carbon dioxide gas. And you already know the star of this equation. It's the hydrogen carbonate ion, our amphiprotic friend from earlier. And here it plays its base role, accepting the H+ from the acid. The products? Salt, water, and a little carbon dioxide, which is why antacids can make you burp. A fierce acid, tamed into salt water and a burp, by one proton changing hands. Every time you see an antacid ad, you're watching Brønsted Lowry theory being sold on television.
Let's gather the whole lesson up. An acid is a proton donor, a giver. A base is a proton acceptor, a taker. One tiny ball, changing hands. A conjugate pair is two species exactly one H+ apart, matched across the arrow like socks. To write any equation, move one proton, drop the giver's charge by 1, raise the taker's by 1, then check atoms and charge both balance. Strong acids get the single arrow. Weak ones hold the ball loosely, so they get the double arrow. Amphiprotic substances play both roles: water, hydrogen carbonate, hydrogen sulfate. And polyprotic acids go down the staircase, one proton per stage, never two at once. Look at the picture on the right. Every single idea in this topic orbits that one gold ball. If any line feels shaky, scrub back to that board and watch it again. That's exactly what the video is for. Your turn now. 5 questions, 1 for each skill from today. Question 1 is pure conjugates. Add or remove exactly one H+ and adjust the charge. Question 2, a strong acid in water. Think carefully about which arrow it deserves. Question 3, match the partners across the arrow. Question 4, you know the code word by now. Amphiprotic means 2 equations. And question 5, count the hydrogens, then take the staircase one step at a time. Pause the video here and work through them slowly, checking atoms and charges on every line. The full answers are on the next 2 boards, but don't peek until your page is full. Take your time. Understanding first, speed later. Let's check your work, slowly. Question 1. Remove one H+ from nitric acid and the charge drops 1 step. Its conjugate base is NO3-. Add one H+ to hydroxide and the charge rises 1 step. Its conjugate acid is plain old water. If you wrote O2- for the first part, you removed a proton and an extra electron's worth of charge. One H+ means the charge moves exactly 1 step, no more. Question 2. HBr is strong, so it throws the ball and never takes it back. Single arrow. Water accepts, hydronium and bromide form, and the charges add to 0 on both sides. If you drew a double arrow, that's the 1 mark you dropped. Question 3. Match across the arrow. Ammonia became ammonium, 1 pair. Water became hydroxide, the other. Notice water is the acid here. Amphiprotic, as always, doing whatever the moment needs. And the last 2. Question 4. 2 equations, remember. First, HS- as an acid. It donates, becomes the sulfide ion, S2-, and water becomes hydronium. Charge check, -1 both sides. Then, HS- as a base. It accepts, becomes hydrogen sulfide, H2S, and water becomes hydroxide. -1 both sides again. 2 balanced equations, proof complete. 1 equation alone was only half the marks. Question 5. Carbonic acid has 2 hydrogens to give, so it's diprotic. 2 stages, 1 proton each. Stage 1. Carbonic acid becomes hydrogen carbonate. Stage 2. Hydrogen carbonate becomes carbonate. And there's our amphiprotic friend one last time, sitting on the middle step of the staircase, exactly where it belongs. If you got all 5, brilliant. If not, find the board that covers the one you missed and watch that pass of the ball again. Great work today. Acids and bases looked like a big topic when we started, and now you know the truth. It's one tiny particle moving from one place to another, and you can follow it anywhere. Next lesson, we look at strong and weak acids properly and the pH scale. Until then, you're mastering VCE chemistry, one concept at a time. See you next time.